Hello students. Now we are going to learn another topic which is also very closely associated with the previous sessions, that is about base kets and transition amplitudes. We have learned in the previous sessions how the state kets and operators vary in Schrodinger picture as well as Heisenberg's picture. Now we are going to see how the base kets and the transition amplitudes behave in both Schrodinger in as well as Heisenberg's picture. Okay, from the previous understandings, we can conclude that the state kets changes in Schrodinger picture while the observables remain the same, right? Whereas in Heisenberg's picture, the state kets remain the same while the observables changes. And how it changes with the time evolution operator and all we have already learned. So just go through that before going into this particular lecture. Now, so we are going to discuss about the base kets and transition amplitudes. So now let us consider that eigenket of an observable. Let A be an operator and let A prime be the eigenket of the operator. We have already learned about the eigenvalue equation, the eigenkets and all. And what you can keep in mind is that eigenket, we know that any state ket can be written in terms of its base kets, right? So eigenket can also be considered as base kets. Now, suppose if A prime is a ket, A prime is a eigenket or a base ket, I can write for an operator A prime equal to A prime ket A prime, where here A prime is the eigenvalue. Okay. Now, this is the equation which I write in the Schrodinger's picture. And now, suppose if it changes with time, what happens? We know that in Schrodinger's pictures, as time changes, the operator doesn't change. And if the operator doesn't change, we can say that if we solve this equation and if the operator A does not change, then the base kets, if the A does not change again, the same eigenket will be obtained as the solution of this eigenvalue equation, right? So we can say that so what I said is if the eigenvalue equation, since the operator doesn't change in Schrodinger picture, so what I will write that this is Schrodinger picture, otherwise you'll get confused. This is Schrodinger picture. Okay, this is for Schrodinger's picture. In Schrodinger picture, you can write the equation for base kets as this. And we know that in Schrodinger picture, capital A doesn't change. If it doesn't change, the solution of this equation will also never change. So as time t changes, we can say that the state ket, not the state ket, the base ket should remain the same. So this is different from the behavior of state ket in Schrodinger pictures. We have seen that in Schrodinger picture, the state ket changes. But now we understand that the base ket will never change in Schrodinger picture. So base ket will never change in Schrodinger picture, but the state kets will change. Okay, so we concluded at one thing. Now we are going to see how the base kets will change in Heisenberg's picture. Okay, now let AH be the Heisenberg's operator. And we know that the Heisenberg's operator with evolution of time changes, right? So that how it changes, it will change according to this equation 2. We can say that Heisenberg's operator AH at a time t can be written as U dagger A at the time 0 and U. So this is how the Heisenberg's picture operator changes. Okay. Now what we can do is now what you do is we can write in this relation. You take the first relation. Okay, first relation for Heisenberg's picture at the time t0. I can write A0 ket A prime equal to A prime ket A prime, where you can see this A0 and this capital A both are same because Heisenberg's picture operator at the initial time is same as the Schrodinger's picture operator that you have already understood, right? So I can write in Heisenberg's picture itself at the time t equal to 0, I can write this relation. Now what happens with time changes? When time changes, we can say that we can find out. So on the process, what we are doing a simple mathematical procedure. Now you operate on the left hand side and right hand side of this equation with U dagger. So I use U dagger on the left. Also in the right hand side of the equation, I introduce U dagger. Okay. Now, in the next step, what you do is you can introduce U dagger in this equation, left hand side of the equation. We know that already U dagger is I identity operator. So if that is so, there is no harm in introducing an I here, right? So I introduce U dagger A0, and here I put U dagger A prime. Then right hand side remain the same. I don't introduce anything on the right. Okay. Now you just see, so I can write. Now let's see on the left hand side, U dagger A at 0, U is what? This is simply the AHT, which we have written in equation number 2. So instead of these things, instead of this much, I can write AH, right? Now then remaining U dagger, A prime and A prime. Right hand side, there is no change. Now you just see H is the operator and A prime is the eigenvalue. Now we have written, so when starting from this equation, with the change in time, we found that we arrived at another relation where U dagger A prime is the base ket, right? So that as time goes on, in Heisenberg's picture, what happens? The operator remains the same, but then what happens? The base gets changed. Base get changed. So base get changed as U dagger A prime. But this is different from the change of this state get in Schrodinger's picture, right? In Schrodinger's picture, state get changed as U A prime. U get A prime. But here in Heisenberg's picture, this base get changes as U dagger A prime. Okay. Now you come to the next equation, next slide. Thus, in Heisenberg's picture, we understood that the base get changes. So how the base get changes? The base get changes as A prime was the base ket at time t0. It changes as U dagger ket A prime. And it becomes like this in Heisenberg's picture. So now we can conclude two things, that the base kets will remain same in a Schrodinger picture and the base kets changes in Heisenberg's picture. So this is contrary to what is happening for the state kets in Heisenberg's and Schrodinger's picture. Now we have seen that instead of U, which appears in the Schrodinger picture, in Heisenberg's picture, when the base gets changes, instead of U dagger come in, right? So we can say that the Heisenberg's picture base gets are seen to rotate oppositely compared to the Schrodinger's picture state gets. Now, similarly, the A prime Schrodinger's the other Schrodinger equation, when we wrote the Schrodinger equation, and that is also different in the case of Heisenberg's picture. In Heisenberg's picture, the A prime base, when we write that for base gets, that will there will be a negative sign arising because of the U dagger coming in. So I can write this when you write the Schrodinger picture for the state ket in Heisenberg's, for the base ket in Heisenberg's picture, you can write it as IH ket dou by dou t A dagger t equal to minus H A prime t. And this is actually the wrong sign Schrodinger equation. Okay, so this is all about the base kets. Now we are going to see the transition amplitudes. So by which transition amplitude, what we mean is that an operator which is at an with an eigenvalue state ket. Let we can say that suppose we have a physical system at a time say t equal to 0, which is in an which is an eigenstate of an observable a with an eigenvalue a prime. So at some later time t, this actually changes to, we can see the system in another observable, the system changes, and it will be in another eigenstate of an observable b with an eigenvalue b prime. Okay, so transition amplitude means what is the probability for the system at an eigenstate a prime to change to an eigenstate b prime. Okay, so in now we are going to see what is the transition amplitude in both Schrodinger as well as in Heisenberg's picture. So in Schrodinger's picture, the state at a time t is given by u ket a prime. I'll show you. You can see in this is the actually the Schrodinger's. Sorry. You just see this, and what is this? This is actually the Schrodinger's picture state cut, right? So now we are going to see the what is the transition amplitude for the state cut to um, change from this state to the eigenstate b prime. Okay, to the eigenstate b prime. We are going to see how the system which is at the eigenstate a prime changes to b prime. So now with as time changes, the state ket, with the evolution of the time, the state ket in Schrodinger's picture can be written like this. So now what happens? We are going to see what is the transition or what is the probability for the state ket to change to the state ket bra. Okay, no, it is we have written as bra b. So ket a prime is one eigenstate, b prime is another eigenstate. The probability for the system to change from a prime to b prime can be written like this. Okay, so we can say that as time changes u a prime, how it changes to b prime. So I can write this thing like this. Now next we are going to see uh, what happens in the Heisenberg's picture. Heisenberg's picture, we know that the state ket remains the same with the evolution of time. So I cannot write u. So I write state ket as this. Now we are going to see how the state ket changes to how this a prime changes to the b prime. Okay, but with evolution of, we can say with evolution of time, a prime doesn't change. A prime remains the same. But with the evolution of the time, with the evolution of time in Heisenberg's picture, b prime changes. And how it changes? We know that b prime changes as u right. So with time changes, u b b prime base ket b prime changes as u b prime. Sorry, u dagger b prime. So u dagger b prime means we can write it as ket. Sorry, bar b prime u. Okay. So as time as time changes, state ket a prime changes to b prime, and how, what is the probability amplitude that you can write like this. And you can see that in both the Schrodinger, this was actually Schrodinger's picture. Okay, and this was actually Heisenberg's picture. We can see that how it changes. In both the cases, the transition amplitude basically is the same. When you write it together, you can say that both the transition amplitudes are b prime, bra b prime, u ket A prime. So this will remain the same. Transition amplitudes remain the same for both Schrodinger and Heisenberg's picture. I'll say this once more. I think you will have a confusion in this part. Here, just listen. We are going to see um, how the function or how the state ket will change from the state A prime to state B prime. Okay. Now the probability for the state ket to change from or the probability for the system which was at state A prime to be found in the state B prime can be basically written like this. Okay, so that is first we write the first state, and second on the left hand side you write the first the next state which it is going to be found in. Okay, so I can write now with time. So this is this we write with the time evolution. Okay, now we say that as time changes, A prime changes as what? As time. This is actually Schrodinger's picture. So the state ket A prime changes as U A prime. Right, in Schrodinger's picture, state ket A prime changes as U A prime. Now it changes to which base ket? It changes to B prime. Okay, so I write the first state with the time